The second part of lesson 6.2 is all about trapezoids. In this lesson, we'll define trapezoid and take a look at its unique characteristics. Scrolling down to the definition of trapezoid. A trapezoid is a quadrilateral with just one pair of parallel sides, which means they would not intersect. So over on the right, let's create a picture that looks like a trapezoid. I'm going to start by drawing a segment on top, like so. And then I want to draw a longer segment on the bottom that's parallel. And then what I'm going to do is just connect from the left side down and then the right side down, like so. Now that is a trapezoid. To designate that one pair of parallel sides, we're going to put an arrow on the top and bottom. Now the top and the bottom are the bases of the trapezoid. It's important to know those terms. The parallel sides are the bases. And the other two segments are just the sides of the trapezoid, like so. And there's your trapezoid. Down below, let's go ahead and get a little bit more specific with some of the particular characteristics inside the trapezoid. Looking at this picture down below, ABCD is a trapezoid. By definition, we can put an arrow on segment AB and an arrow on segment DC. That means they're parallel to each other. Now, just like up above, we defined the four sides of a parallel like so. AB is a base. Even though it's on the top of the picture, it's one of the two bases. CD is the other base. Again, AD, since it connects those two parallel edges, is just a side of the trapezoid, and then so is BC. Please make sure to add all of this into your note packet because as we move on, we're going to look at another type of trapezoid that has more defining characteristics. Okay, so what else we know is that angles A and D, since they're on the same side of that segment, I'm going to put an arc on angle A and a double arc on angle D. Those are called same side interior angles. And we learned about those way back in topic 2. And I'm just going to abbreviate angles with like a little angle symbol. The rule is if they're same side interior angles, then the measure of angle A plus the measure of angle D is equal to 180. If the two on the left side are same side interior angles, the two on the right side would be as well. Angles B and C are also same side interior angles. And they too would have a sum of 180 degrees. Now here's one thing to note. On a trapezoid that isn't more specific than this one, A and B have no connection. C and D really have no connection either. That means we'd have to put maybe like a triple arc on B and then a quadruple arc on C, just to prove that they aren't connected to A and D in any way. And that's kind of the basics for sides and angles in a trapezoid. Let's go back up quickly though to that mid-segment definition before we go to the next page. A mid-segment of a trapezoid is a segment that connects two midpoints. And what we're going to do is take midpoints of each side of the trapezoid. So we're going to write midpoints of each side. And then we're going to connect it. Let's draw a picture on the right. I'm going to start off just kind of by copying the picture that's up above to get the visual of a trapezoid. We don't need to put the capital letters on there or anything. We're just going to define what that mid-segment means. Now remember, the sides are the left-hand side and the right-hand side. What I'm going to do on that left-hand side is approximate where I think the midpoint would be. So I'm just going to put a dot there. To prove on the picture that that point cuts that side in half, I'm just going to do a dash on either side. So let's maybe make that point a little bit more prominent like a dot, and then those dashes. Over on the other side, I'm going to do the same thing. Approximate where I think that midpoint would be, Now that side's going to be different, so I'm going to give that one a double dash on the top and bottom. If we connect those two midpoints, that segment is called the mid-segment. And as we work through the lesson, there are going to be some pretty unique characteristics about that mid-segment. But for now, let's flip it over to the next page. A unique thing can happen with a trapezoid if the two sides are also congruent. This is known as an isosceles trapezoid. So the main trapezoid is JKLM. If this is an isosceles trapezoid, there's so much to know, everybody. First things first, we know that JK is parallel to LM. That's just definition of a trapezoid. But then to be more specific for an isosceles trapezoid, JM, the side, is also congruent to the side KL. That's new for us. That wasn't like that before. Also, what else do we know? We know that angle, let's go with angle M first. Angle M would be congruent to angle L, and angle J is congruent to angle K. Along with J plus M would equal 180 and K plus L. So lots of things happening here. Something new that we haven't drawn in yet in this lesson would be the diagonals. So let's take a dashed segment and connect from J all the way down to L. That's diagonal JL. And let's go in the other direction from M to K. Same thing, like so. And guess what? Those diagonals are also congruent. Lots of information here. So that would mean segment JL is congruent to segment KM. So that's important to know. Let's see, what else do we know about this picture? Well, that mid-segment is drawn in, so another thing we could say, if N is the midpoint of JM, we know that this is true and this is true. We also know that this is true and this is true. Since NP is the mid-segment of the trapezoid, it is also parallel to the top and the bottom. Now, we also have a formula. Boy, there's lots happening with this isosceles trapezoid. The mid-segment, so the length of NP, is going to be half of the two bases. So a half of JK plus LM. So in general, hang tight. Let me fix that letter here. So in general, if you take the two bases, add them together and divide by 2, that's going to be the value of the mid-segment. And we'll use that formula later on in some examples. All right, let's go to the last or the next example that we haven't covered yet related to trapezoids. Please try to find example 3. This is the last example, or this is the example that we didn't do in our notes last week. It says, given isosceles trapezoid PQRS. Let's go ahead and underline isosceles because we know some unique things about that. It says, what are the measures of angles P, Q, and S? So we're trying to find the measures of just the rest of the angles. We know by definition that the two lines are parallel. That would make angles R and S supplementary. They form that same side interior. So to get angle S then, if we just do 180 minus 135, well, that's a 5. There we go. S would equal 45 degrees. Easy enough. But then that word isosceles, remember that lets us do a couple other things. In an isosceles trapezoid, the two angles at the top are the same. So angle Q is equal or congruent to angle R. That makes angle Q 135 degrees. Pretty easy. And then down below, angle P on the left-hand side is going to be congruent to angle S. That's a unique rule about isosceles triangles. All right, let's take a look at the example on the right. 3b says, given ST is parallel to RU, Because of this statement right here, we can put a little arrow on the top and on the bottom. That makes STUR a trapezoid. It says, what is the measure of angle TUR? If we go from T down to U over to R, we're looking for the measure of this angle on the bottom right-hand side. Now, what do we know about this picture? We know it's a trapezoid, and see the dash on SR and TU? That means it's an isosceles trapezoid. And that's going to be helpful. Now, the 47 really isn't on the inside, so that's not going to do us a whole lot of good, except for the fact that if the 47 is on that left-hand side, then angle SRU over here on the right is a linear pair. If we can find that angle, then we know the angle of TUR. If we take 180 minus 47, we would get angle SRU to equal 133 degrees. Now, if that angle is 133, then angle TUR is also 133 degrees. So the measure of angle TUR is 133 degrees. Let's try example 4. All horizontal beams of a high voltage transmission tower are parallel to the ground. What that tells us is we can mark this top edge, that longer bottom edge, and even this edge down here. Those are all parallel beams. It says the top section is an isosceles trapezoid, and so is that center section. So see where it says 10 on the left? I'm going to put a dash there, 10 on the right, and then down below where it's 14, I'll place a double dash, and then a double dash on the right-hand side as well. It's kind of like we have an isosceles trapezoid on top of another isosceles trapezoid. If the measure of angle 1 is 138, what is the measure of angle 2? I'm going to zoom out that picture so we can kind of get a better visual of what's going on here. All right, so here's that tower station. It says the measure of angle 1 is 138. If I put an arc right there and make that 138, then we know over to the side that's also 138. Now to get the two angles on the bottom where angle 2 is located, same side interior angles are supplementary. They add up to 180. If we take 180 minus 138, we would get a value of 42 degrees. That's a degree symbol right there, kind of. Okay. I'm just going to fix that. Sorry. I don't like to see that there. There we go. That's going to be the measure of angle 2 down below. So the measure of angle 2 equals 42 degrees. Now the second part of this is going to talk about the diagonals down below. So let's take a look. One cross support in the center of the tower measures 4C plus 3, and the other measures 6C minus 5. What is the length of each cross support? Well, if we look at those cross supports, those are diagonals. And remember, in an isosceles triangle, diagonals are congruent. And what that means we can do is we can take 4C plus 3, set it equal to 6C minus 5. And now it's just a little bit of algebra. We've got a C variable on each side of the equation. Let's take the smaller one and move it over to the bigger one. Cancels that out on the left, but we still have a 3. On the right-hand side, 6C minus 4C, we have 2C left over. But now we have to move the 5 to the left. Let's add that. 3 plus 5 is 8. And last step, to get C by itself, 8 divided by 2 is 4. Now that's the variable for C, or that's the value of C. We want to know what the actual cross support is. So if I plug it back in, 4 times C plus 3, 4 times 4 is 16, and 16 plus 3 is 19. And from the looks of it, it looks like our label is going to be in feet. So that means the diagonals of that trapezoid are 19 feet. We have just one more example. It says the manager of a trapezoidal dog park that always makes me laugh, wants to build a fence to separate the park into a small dog and large dog area. What is the length of the new fence? So the fence that we're looking at is that dashed fence in between where the small dogs and the large dogs go. Now it's defined as a trapezoidal dog park, so we know that the top and bottom are parallel. What I also notice is that you've got 60 on the top and bottom of that left-hand side. That means we're at the midpoint. And 65 and 65 on the right-hand side means we're also at the midpoint. The fencing is going to be the mid-segment. And remember our formula for mid-segment, we're just going to take half times the sum of the two bases. And we know those measures. They're 70 and 120. If we add them together, 70 plus 120 is 190. 1/2 times 190 is 95. And again, looking at the picture, it looks like our label is going to be feet. If the fence is 95 feet long, that would be the mid-segment of that trapezoid. And here is the last part of lesson 6.2.